Hi all. We're going to continue the discussion with the solution of a system of linear system of ordinary differential equations. So we're going to assume that we have a system of the form x prime equal to ax, and we will discuss the different forms of solutions that are possible based on what matrix A we have here. And I'm going to start with the most basic solution for this type of equation, and that most basic solution is something of the form xi e to the rt, where xi is an eigenvector of the matrix A, and r is an eigenvalue. I'm not going to do the derivation because we have seen this infinite times in earlier lectures. You can plug this in the equation x prime equal to ax, and you can immediately see that r is an eigenvalue and xc is an eigenvector. Now, obviously, we will see that the nature of solution depends in many ways on what type of eigenvalues we have. If they are real, are they positive, negative? If they are complex, do they have a positive or a negative real part? And also, if we have eigenvalues that are repeated, how many independent eigenvectors can we actually extract for our system of interest? So let me jump to slide 55, and we're going to take a very particular system that looks like this. So our matrix is 1, 1, 4, 1. You can go and compute the eigenvalues, and the eigenvalues can come in this case to be 3 and -1. So there are two eigenvalues of different signs, and the two corresponding eigenvectors are 1, 2, and 1, -2. So what I'm actually plotting here on the phase plane are the two eigenvectors. In principle, if I denote these eigenvectors here as xc1 and xc2, literally the solution x1 corresponds to the line xc1. So x1, 2x1 equal to x2, and this corresponds to the line defined by xc2. So what do these lines mean? So let's take a very particular case where, let's say, we start a trajectory being on the line xc1. So if we're on this line, it means that c2 equal to 0, and we only have c1, and you can see at increasing time as t goes to infinity, the solution diverges to infinity, but you stay on this line defined by the eigenvector xc1. Similarly, if you start with a location on the eigenvector xc2, this is here xc2, you can see immediately that the solution converges asymptotically to 0, because e to the minus t as t goes to infinity gives you the value 0. So again, we have two characteristic directions. The trajectories go to infinity if we are on xc1, and they go to 0 if we're in xc2. So in principle, the solutions that we get when we start on the line xc1 are unstable, and the solutions that we get when we start on line xc2, they're stable, asymptotically stable as we go to 0. Now, for any other values of c1 and c2, the trajectories look like this, and immediately you can recognize that this is the dominant term as t goes to infinity. So all the solutions, as you can see, as t goes to infinity, go to infinity. And depending on c1 being positive or negative, this can be plus infinity or minus infinity. So this particular case that we have two eigenvalues, one here being positive and one negative, is what we call a saddle point. So the critical point 0, 0 is called a saddle point, and this has much to do with these two characteristic directions, where in one direction we go to infinity, and in another direction we're actually asymptotically approach the critical point 0, 0. Obviously, this situation here is unstable because all the trajectories go to infinity, except, of course, again, if we start on some initial state on the line defined by C2. In that case, we go to 0, but all other cases, basically, they will go to plus minus infinity. Okay, let's consider now another case. So we're going to go to slide 64. I have only changed my 2x2 matrix to be what you see here. You need to trust me if you compute the eigenvalues that you're going to get an eigenvalue lambda equal to 1 and lambda equal, lambda equal minus 1 and lambda equal minus 4. And these are the two corresponding eigenvectors. So you can actually see when you take, so these are the two characteristic lines, similarly as before, and you can see if you start, let's say on the line x1, because of this e to the minus t, you will approach asymptotically the critical point 0, 0. And similarly, if you start on anywhere on the line x2, you will asymptotically move towards the critical point 0, 0. In any other line, if you look carefully, this plot indicates that you are actually approaching asymptotically the point 0, 0 in a direction that is tangent to x1, and that is to be understood because if you look at this general equation, when t goes to infinity, the dominant term is e to the minus t. This thing dies, the e to the minus 4t dies way faster, so the dominant solution is e to the minus t, which means the slope of the trajectories coincide with the trajectory defined by the eigenvector C1, 1 square root of 2, as you see here. So in this case, we call this the critical point 0, 0. We call it a node. And obviously, you will agree with me that this node is asymptotically stable because every trajectory basically reaches, as t goes infinity, reaches this critical point. Let's look one more different case. So in this case, I don't show you what the actual matrix is. So what the only thing I am telling you is that you can see from the general solution here that the two eigenvalues R1 and R2 are the same. So we have a repeated eigenvalue, and I'm making the assumption that the two eigenvectors corresponding to this repeated eigenvalue are distinct. In general, as we know, this will not be the case, all right? So here we are assuming that C1 and C2 are distinct. And I see in this picture an example with these dark vectors of a vector C1 and C2. So what is particular on this case where we have two repeated we have an eigenvalue that is repeated. You notice that in this case, if you start at any location, your trajectory will be a straight line towards the origin. And I'm assuming here R is less than 0, by the way, so that way we can get a stable situation. So if we start from any point, the trajectory will be a straight line towards 0, 0. And of course, that straight line will be defined in terms of C1, C2, C1 and C2, and the time is not coming in the picture because when you compute x2 over x1, the e to the RT's terms will cancel out. So effectively, we have the situation that you see here with star-like looking trajectories, where if you give me a vector d here, this can be actually the tangent of a trajectory that follows this line towards 0, 0. And similarly, if you take a line, that line defines a tangent as I go 0, 0, and every orientation is the tangent of a trajectory from one point on the x1, x2 plane towards the 0, 0 critical point. So this is what we call a start node. And on the plot on the right, you see that if you plot x1 versus t, it doesn't matter from where you start, you asymptotically approach 0. And again, this is with the case R negative. and having a double eigenvalue, but two distinct eigenvectors. Now, if r is greater than 0, you will get actually the same situation as you see on the left. The only difference is that all the trajectories will take you to infinity, so the direction of the arrows that you see in this picture will basically change to take you to infinity. All right, so let me consider still another case. This is with a 3x3 matrix. So let me go to a matrix A that looks like what you see on the slide. So obviously here we have 3 eigenvalues and 3 eigenvectors, and it comes out that 2 of the eigenvalues are the same, so similar to the situation we had before, but actually you can compute 3 distinct independent eigenvectors that I call them here X1, X2, and X3. Now, in many ways, you can see because of the presence of an eigenvalue equal to 2, if you start from some random point in the space, in the three-dimensional space, effectively the solution X1 e to the 2t will dominate, and it will take you to infinity. So basically the situation that you will get will be an unstable situation. But there is a special case that if you start with, let me just give you the slide. So if you start with an initial condition that lies on the planes of the vectors X2 and X3, then effectively you will stay on that plane. And because the corresponding eigenvalue is -1, and you have this e to the minus t terms, then all the trajectories on the X2, X3 plane will actually approach the critical point 0, 0, 0, so you get a stable situation. In any other case, starting from anywhere else, this e to the 2t will dominate, and effectively you will get a solution that is unstable. All right. How about when we have complex eigenvalues and eigenvectors? So here what you see is you see 2 eigenvalues, lambda plus I mu and lambda minus I mu. I remind you that complex eigenvalues come in pairs, that they're conjugate to each other. And the same thing is true with the eigenvectors. So we have X1 that is some vector A plus IB, and some vector A minus IB will be the eigenvector corresponding to lambda minus I mu. So you can actually start with a very general solution. For example, you can say one solution will be A plus IB e to the lambda plus I mu t, and similarly for the vector C2. But if you combine those two solutions, you can find two real fundamental solutions, and they look like what you see on the equations on the bottom. So e to the lambda t, A cos mu t minus B sine of mu t, and similarly here with a plus sign. So basically what we have is we have an exponential growth or decay depending if lambda is positive or negative, and then we have some oscillation defined by mu, and I remind you lambda is the real part of the eigenvalues, and mu is the complex part of the eigenvalues. So basically, these are our two fundamental solutions. And if you ask now how these trajectories look for this case with two complex conjugate eigenvalues, the answer is very simple. So let's do one example. If I take this matrix with this particular elements, you can actually compute the eigenvalues. And the eigenvalues, I'm guessing here, they will come to be -1/2 plus minus I. So you can extract two real solutions, and I am giving you here the corresponding solutions. One of them is this vector that you see here, and this is another vector. So effectively, if you plot the trajectory starting from an arbitrary location in the x1, x2 plane, every trajectory in this particular case will actually approach 0 because of this exponential e to the minus t over 2, but it will approach 0 in an oscillatory manner because of the sines and cosines of these. So the trajectories will look like what you see on this picture. And all the trajectories for this particular case will actually approach the critical point. So this critical point is obviously an asymptotically stable point. You can actually have a different situation where the real part, instead of being minus 1/2, is plus 1/2. So the trajectories will look similar to what you see here. The only difference, of course, will be all the directions of the arrows here we have to change, and all the trajectories will basically go to infinity, and you will get an unstable point. This type of trajectories, obviously, because of their shape, we call them spiral trajectories, and the corresponding critical point is called a spiral point. So you can think of having an asymptotically stable spiral point the way you see in this picture, but also you can have an unstable spiral point if the real part of the conjugate eigenvalues is positive. Now you may ask, can I actually get these spirals, instead of looking like this, can they actually look circles? And the answer is yes. If it happens that the eigenvalues that you get, they are pure conjugate numbers without any real part, then obviously the trajectories will be circles. And I'm going to show you a situation that looks like that. This is a case. You can immediately see here the two eigenvalues are plus minus 2i, and these are the corresponding eigenvectors, and effectively all the trajectories are circles. And notice, because they are circles, you can think that this is the critical point 0, 0 is a stable mode, but notice is not an asymptotically stable mode. So effectively asymptotically stable means you look at the trajectories and you want them to approach the critical point. In this case, they don't approach. If you think of a particle in each of these trajectories, this particle will keep going on circles forever without ever approaching 0, 0. So this is a stable center mode, but it's not asymptotically stable. All right, so let me change a little bit topic for 1 second and talk a little bit about the solution of the system of equations x prime equal ax, and trying to introduce what's called the fundamental matrix psi. So let me just go to slide 113. And so we have a system of equations. I don't know why from A we went to P here, but it doesn't matter. We have a system of equations that looks like this. We compute n fundamental solutions x1 to xn. And you will agree with me that this linear combination of the fundamental solutions, I can write this in a matrix form. A matrix psi times the vectors that consist of the scalar C1 to Cn. And this matrix, what is this matrix? Each column of this matrix is one of the fundamental solutions. So this is x1, this bold x1, and this is this bold xn. So that's my fundamental matrix, all right? And what you see here is the solution to my system of equations, because I'm assuming here that the solution, it's written as a linear combination of the fundamental solutions x1 to xn. Now, since this is an initial value problem, you may say, where are the initial conditions accounted for? And the answer is very simple. Let me go directly. You remember our general solution is psi at time t times the constant c. C is independent of time. So if I apply this at time t0, psi at time t0 times c has to be my initial state x0. So c is equal to psi inverse t0 x0. So my general solution for initial condition x0 is given by this nice formula that you see on the bottom. So if you know this fundamental matrix psi, and you compute the inverse at the time t0, at the initial time, so this matrix times x0 will give you the solution of x prime equal this matrix P times x. Now, I'm going to ask you something that we discussed this in another lecture. Do you remember a nice way to generate n fundamental solutions x1 to xn for our system of equations? That very nice way of doing it was to actually start with initial conditions that look 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1. So if you start with these initial conditions, the solutions to our x prime equal to ax form a set of fundamental solutions that you can use actually to define the matrix psi. You may say, and what is interesting about this particular solutions corresponding to these initial conditions? Well, here is what is important. In that case, the matrix, I call this matrix of the fundamental solutions here phi to distinguish from psi, because there is special thing about this matrix, and the special thing is that the initial condition is the identity matrix. So if you remember before, we wrote the solution as psi inverse calculated t0 x0. Now this matrix here is equal to the identity, so my general solution x is phi of t x0. So we don't really have to do the inversion of the psi matrix, because in principle that inversion is contained inside the calculation of this matrix phi that you see here. So in principle, this matrix phi at time t is nothing else but psi of t times psi minus 1 at t0. All right, so let me do an example to see what all these things mean. So let me take a system of equations that looks like that. So this is my matrix. So I am going to try to generate the matrix phi. So what I'm going to do is I'm going to generate two fundamental solutions. How do I do that? I am going to start with two different type of initial conditions. X1 at 0 will be 1, 0. X2 at 0 will be 0, 1. And for each case, for this particular case, initial condition 1, 0, I'm going to solve this equation. And the solution x1 that I'm going to compute will be one fundamental solution. And then I'm going to repeat and compute another fundamental solution for initial condition 0, 1. Then take those fundamental solutions, put them together as the columns of the matrix phi, and we will immediately see what the matrix phi is all about. So let me see if I can being able to show you what this matrix phi is. So when you do all these calculations, right, you need to find the fundamental solution. So here is on the bottom, you can see what the solution x2 is when the initial conditions are 0 and 1. So when you put all of this together, this is the matrix phi that comes in your problem. And so it looks obviously a little bit more complicated. And actually, if you go and visit the complete set of slides, you will see that the matrix psi, it's less complicated. It looks like this, but don't remember to get phi is the same as multiplying psi with psi at time t0 inverse. So obviously there is an inverse that you have to calculate, and then multiplication by psi, and that information is contained on this matrix phi. Now, what is the value of all of this? If you have phi, you can actually solve the system of equations x prime equal to ax for any initial conditions. And what is the solution to the system of equations if you have any initial conditions? The solution is basically this matrix phi times x0. So if you multiply phi with any initial conditions, you will get the solution to your system of equations for that initial condition. In principle, in case you have not realized this, if you have x prime equal ax, the solution is really e to the at, so it's the exponential of a matrix, e to the at times x0, which means that actually this matrix phi that you see here is the same as the exponential matrix e to the at that we have seen in earlier lectures. and also I remind you it was part of in one of the problems in exam 2. Okay, let's talk a little bit more about the solution of this system of equations. So, so what I want to do is, and actually I can go directly on the bottom of the slides, I want to remind you the similarity transformation. So if I have a matrix A, and I multiply in this case with the Hermitian of T, which is T inverse, I can diagonalize the matrix A. I remind you, when we discussed this in earlier lectures, we use the orthogonal matrix of the eigenvectors Q. Here I indicate in this set of slides this with the matrix T. So T is a matrix that has in every column one of the eigenvectors. So when I say T star, if the matrix is symmetric, you don't really have to invert the matrix T, because Q transpose, T transpose will actually do the job. Okay. But what I want to use here is that I can diagonalize a matrix A by this similarity transformation T star AT equal to D, where D comes to be a diagonal matrix. And so you may say, how is this useful for a system of ordinary differential equations? Let's see this. So what I'm going to do is I'm going to go to slide 133, and let me take this system of equations x prime equal to ax. I am going to transform the system from a variable x to a variable y, where x is t times y. And I remind you again, T is a matrix that has in every column one of the eigenvectors of the matrix A. So I am going to substitute on x prime equal to ax. So x prime will become ty prime that you see here. Then I have a times x, and x is ty. So I can multiply with t inverse, and then I have y prime, thus dy over dt equal t minus 1 at times y, and t minus 1 at is diagonal matrix D. So effectively what I have done is I started with a system of equations that they are coupled, and I have actually transformed this system of equations to an uncoupled system of equations for the variables y. Obviously, you can solve those. You will have n scalar ordinary differential equations that they are uncoupled, that you can solve, and once you compute y, your solution x will be nothing else but t times y, and then you're done. So what is the solution now of y prime equal dy, right? Since my equations are uncoupled, the solution is really nothing else but what you see here is e to the lambda 1t, e to the lambda nt. So I'm taking here the case of having n distinct eigenvalues. And there will be other versions, depending on what the situation looks like. But in the simplest case, the solution to this diagonal uncoupled system of ODEs is this exponential matrix. And then if you want the solution x to the original system of equations, then the solution would be nothing else but actually multiplying the vector with the matrix with the eigenvectors in its diagonal with this exponential diagonal matrix. And this is my fundamental matrix from my original system of equations. Okay, so basically we have been able to solve with diagonalization quite easily this system of coupled equations by transforming them to a system of uncoupled equations. Okay, there is an example in the notes if you want to see a little bit more details. So let me proceed a little bit and discuss the situation with repeated eigenvalues that we have seen before. So let me take again x prime equal to ax. This matrix, as right here, A without the x here, A is this nice matrix 1, minus 1, 1, and 3. And you can immediately see that it has a double eigenvalue 2 and only has one eigenvector. Obviously, to be able to discuss about the fundamental solutions and the matrix psi that we had before, and the solution of the system of ODEs, we will need another eigenvector. So we don't really have another eigenvector in this case. There's only one eigenvector, 1 and -1. So what type of another independent solution can you look for that corresponds to the eigenvalue lambda equal 2? And you can extrapolate this from the way we solved differential equations before. How about if we try a solution that it is C, which is this eigenvector here, e to the 2t, exactly as before, but times t. So without doing the algebra that is given in the slides, I can tell you that if you try to solve this system of equations x prime equal to ax with a solution that has this t there, you realize that this will not work for you. So in this case, we will basically need to do some better guess than x equal c times t e to the 2t. And that better guess is a solution that will look, if I can find it, that solution will look like what you see on the bottom of this slide. So yes is going to have a component that is c times t times e to the 2t. But in addition to that, it's going to have some other vector, eta, e to the 2t. And that vector eta obviously is not going to be an eigenvector because we said for our metrics we can only define one eigenvector c. So we don't really know what eta is, so we're going to have to compute it. So what we're going to do is the following. Take this trial solution to see if this is going to work, and we're going to differentiate this with respect to time t, plug in this in x prime equal to ax, and equate different terms on the left and the right, so terms that don't involve multiplication by t and terms that have only the exponential, and then see what we get. And what we get actually is something that looks like the two equations that you see on this slide. So you discover that C is an eigenvector, which is already known, right? This is how we started. And then you discover that eta solves this nice equation that looks like an eigenvalue problem. The only difference, the right-hand side is not 0, it's the eigenvector C that we started with. So the problem that you see here, a minus 2i times eta equal to c, is what we call a generalized eigenvalue problem. I remind you that here lambda equal to 2 is the duplicate eigenvalue that we have, all right, and c is the corresponding eigenvector to this particular problem. So let me do one example. I'm only going to give you the results. So if your matrix A looks like this, you can compute the eigenvalue here is 2. You can compute one eigenvector only that has components 1 and -1. So if you solve the generalized eigenvalue problem, it comes out to be eta 1 minus 1 minus eta 1, where eta 1 can be an arbitrary constant. So I can take, for example, eta 1 equal to 1, and then eta will be 1 and -2. But what I have done is here, and this requires a little bit of attention, I split this vector in two components, one that is in the direction of 1 minus 1, and whatever is left, I put it in here. So whatever is left is 0 minus 1. So and k is an arbitrary constant, okay? Now, why do I spell out here the 1 minus 1 vector? Because 1 minus 1 is my original eigenvector c. So the reason we write eta like this is to be sure that the second fundamental solution we get for our system of equations, we need to be sure that does not contain the first fundamental solution. And a good way to do this is by extracting the eigenvector c the way that I have done in this slide. So basically, if you put things together, you remember my second solution will look like this. So if you plug in eta to be what I saw you before, you realize, so this is the ct e to the 2t term that you need. This is from the previous slide, the first term, and this last term, you notice is nothing else but the first generalized solution multiplied by k. So it really is not a useful part for the second fundamental solution. So we really don't need this part at all, and we can only keep the first two terms. So if I can write this at the end of the slide, x2 is going to look like you see on this slide. So effectively what we have is we have x1 and x2, and you can actually now with confidence take the linear combination of these two fundamental solutions that you see on the bottom, and there is a verification on the middle of the slide with the calculation of the Wroskian here. You can see that these two solutions are actually independent of each other, so you are safe. And the general solution to our system of two ODEs, coupled ODEs with a matrix with a repeated eigenvalue is given, as you see on the slide, on the equation at the bottom of the slide. Now, how about if you try to actually plot trajectories for this case? Obviously, you can see in general, because of this term e to the 2t, that the solution will actually, all the trajectories will move towards infinity. And also you can appreciate that the dominant term, as t goes to infinity or t goes to minus infinity, is defined by this component here. And again, I remind you, this is xc times t to the 2t. So all the trajectories basically, as t goes to infinity, will follow this vector, the direction of this vector xc. And so typical trajectories that you see here in this case, and this is a situation of an improper node with a duplicate eigenvalue that is positive. So there is more discussion on the slide, but basically the trajectories are the way that you've seen here. Okay, so let me just proceed to slide 162. And since we talk about diagonalization, somebody may ask, all right, if your system is non-homogeneous, can you still use diagonalization? The answer is, of course you can. We're going to do the same transformation that we worked on before. So we're going to introduce x equal ty. T is the matrix that contains the eigenvectors of A. Plug in this transformation to our non-homogeneous system of equations. And the only thing you need to define is a vector h that is t minus 1g. So effectively, before we had y prime equal dy, and we got a diagonal y with component c to the lambda 1t to the lambda 2t. Here what we have is we have a decoupled system of ordinary equations, differential equations for y, but there is a forcing term h of t in each equation. That is not a major deal, right? We know how to solve non-homogeneous scalar ODEs, and if you want to see the solution, here is the solution. So this is how the equations look like, each of them, okay? This is the general solution. And you notice the general solution has a homogeneous part and a particular solution. So if you get y, you can multiply y by x, your x matrix. I'm sorry, you can multiply y with the t matrix, the matrix of the eigenvectors of A. Then you can get the general solution x to your non-homogeneous system of differential equations. There is other methods that somehow you can actually use to solve a system of ordinary differential equations. So let me give you very briefly two of these methodologies. Suppose that somebody gives you this system of equations to solve. And so what I have done is, so there is a non-homogeneous term that you see here. It involves 2e to the minus t and 3t. I can tell you that this matrix has an eigenvalue, a double eigenvalue to minus 1. So what I have done is I have actually split this forcing term to two terms, 2, 0, e to the minus t, and 0, 3, t. And the reason is because I want to guess particular solutions corresponding to each of these terms, right? Here is this forcing term is some vector times an exponential, but you have to be careful because this exponential contains in the exponent the eigenvalue, and you remember what that means, right? We cannot assume a solution of the form a e to the minus t because that is a part of the homogeneous solution. And similarly here we have a linear term, 0, 3 times t. So here is what the trick is. You're going to assume a general solution that looks like this. So if we call this vector A and we call this vector, well, actually, I'm sorry, let me, we don't call anything A. So this vector is 2, 0, this vector is 0, 3. So we're going to assume a solution that contains the terms e to the minus t and e to the minus t, multiply with vectors to be calculated A and B, and we're going to assume a particular solution for this that involves a linear term in t with some unknown vector c, and a constant term independent of t with some unknown vector d. If you read the remaining of the slides, you will see that once you plug in this particular solution to the system of equations, you will be able to identify what A is, what B is, what C is, and what D. And so you have a particular solution. You can add to that a homogeneous solution, and then you have the complete solution to this non-homogeneous system of equations. Effectively, with this method of undetermined coefficients, the only thing I want you to pay attention, if you have a forcing term that involves an exponential with the eigenvalue there, e to the minus t, the solutions you're going to have to guess, they're not only going to be t to the minus t, but it has to involve the term e to the minus t. If you try alone a t e to the minus t, you will see it's not going to work. You will actually get an issue in calculating the vector A, but if you add those terms together, you will see you'll be able to identify A and B. And similarly here, if you have a linear in t term, you're going to need to have both a constant term and a linear term in C. And again, the algebra is given in the slides, so you can actually follow them through a particular example. So let me just finish these methods for the non-homogeneous problem with another methodology that has to do with the method of variation of parameters that we have seen for solving differential equations. So I remind you, for the homogeneous system, the solution was the fundamental matrix psi times C. So what we're going to do is we're actually going to assume that the solution is psi times some unknown vector u of t. And u of t has to be computed. Okay? So we change the solution of the homogeneous problem from having the constant C to some unknown vector u of t to be computed. So what I'm going to do is I'm going to take this particular solution that you see here, and I'm going to plug it in my non-homogeneous equation on the top and see what happens. So when you differentiate this, right, so you're going to get psi times u and psi times u prime. That's what you see here. And then you have the matrix P times psi times u plus the forcing term G. And I will ask your attention here that psi prime is equal to P times psi. And you know why? Because what is psi? Psi is a matrix that has as columns the n fundamental solutions of our homogeneous system. So effectively, each of the columns of the matrix psi satisfies the homogeneous equation x prime equal px, which means the whole matrix psi satisfies psi prime equal p times psi. So the first and the third term cancel out, and what you get is u prime equal psi inverse g of t. And if this is u prime of t, you can integrate. So if you have u, psi times u will give you a particular solution, and psi times u that you see here on the bottom is the particular solution, that integral. And then you add to that the homogeneous solution psi times c, and there is the full solution to the non-homogeneous system of ordinary differential equations. So effectively, we have three different methods that you can use in solving this system of non-homogeneous equations. All right. So what we're going to do in the next lecture is, if I can go directly on a schematic that is going to be essential to our next lecture. This is what we're going to do. We're going to take a system of two-coupled ordinary differential equations, so x prime equal ax, and we're going to summarize all the previous results of the different type of solutions that somehow you can get, and we're going to summarize them in a graph that contains as axis P and Q. And what is P? P is the sum of the two eigenvalues of the matrix A. And what is Q? Is the product of the two eigenvalues. And somehow, you know, if you know the sum and the product, actually that defines the eigenvalues of the problem, because I remind you the characteristic equation here is lambda squared minus p times lambda plus q equal to 0. So we will see that everything we discussed refers back to this picture. And looking at different locations in this picture, we can see, for example, that on the right here, we're getting basically unstable modes. And on the top of this curve that defines this equation, p squared minus 4q equal to 0, we can see that on the top we have an unstable spiral point and an unstable node to the right. And if you wonder what delta is going to come to be, you remember from the characteristic equation, delta equal to 0 is basically the characteristic equation that defines complex versus real eigenvalues. Okay, and you notice on the top, obviously here we're getting complex eigenvalues, and obviously here we're getting real eigenvalues. Anyways, we will discuss this in detail, and we will see how for your problem you can look at this nice picture, compute P, compute Q from your matrix A, and immediately say something about the nature of the solutions without ever having to solve the equations. This is quite remarkable. It will allow us to discuss the nature of solutions without actually having to solve the solutions, find explicit formulas for the solutions. And again, the picture that you see here is nothing but basically a discussion on the nature of the eigenvalues that you get from the matrix A, and we will see this in the lecture on Wednesday. And again, you can see here we have all the cases of eigenvalues being real, of the same sign, positive or negative, real and opposite signs. And then, of course, we have the case of eigenvalues being complex numbers, and then eigenvalues that are pure complex numbers, corresponding to, as we have seen, to this center critical points. All right, so I'm going to stop there, and we will continue on Wednesday with more discussion on the stability of x prime equal ax and of the different trajectories. And then I'm going to give you sort of a few simple examples indicating how we can use these ideas for linear system of equations and generalize it to nonlinear system of equations using concepts of linearization So we can actually address some real practical problems that are nonlinear in nature. Until then, see you Wednesday.